Hello everyone. Welcome to the third video of week 2. In this video we will further explore the notion of unbiased estimator and illustrate the use of the mean squared error to compare the performance of two estimators. Consider independent x1 up to xn and suppose that each xi has the same expectation mu and variance sigma squared. In the previous video, you learned that the sample mean is an unbiased estimator for mu. Then what about the sample variance? Is this also an unbiased estimator for sigma squared? Well, to find out, we determine its expectation. Using linearity of expectation, this can be written as follows. But the precise computation of the expectation of the sum is a bit involved. Although this can be done by elementary probability theory, we will not pursue this here. You are invited to do this in one of the exercises. But it turns out that the expectation of the sum is equal to n-1 times sigma squared. Therefore, after dividing by n-1, we end up with sigma squared. So the sample variance is an unbiased estimator for sigma squared. Note that this explains why we divide the summation in Sn squared by n-1 instead of dividing by n itself. If one divides by n, then the resulting estimator becomes smaller, and it will have negative bias with respect to sigma squared. So Sn squared is an unbiased estimator for the variance sigma squared. Now, does this mean that Sn itself is an unbiased estimator for the standard deviation sigma? Now, this would be the case if the expectation of Sn is equal to sigma. Well, let's find out. We just learned that the sigma squared is equal to the expectation of Sn squared. Now, the function x squared is strictly convex, and therefore, according to Jensen's inequality that you have learned in probability theory, this means that the expectation of Sn squared is strictly larger than the squared expectation of Sn. After taking square roots on both sides, we find that the expectation of Sn is strictly smaller than sigma. This means that Sn has negative bias with respect to sigma. Therefore, although Sn squared is an unbiased estimator for sigma squared, Sn is not an unbiased estimator for sigma. This example illustrates that if t is an unbiased estimator for some parameter theta, then g of t is not necessarily an unbiased estimator for g of theta. There is one function for which it is true, and that is when g is linear. In that case, linearity of expectations ensures that unbiasedness carries over. Let us continue with the mean squared error. You have learned in the previous video that the mean squared error can be decomposed into the sum of the variance plus the squared bias. Therefore, in general, a good estimator should have both small variance as well as small bias. Now, unfortunately, these two properties do not go hand in hand. Some estimators have zero bias, and in that case, the mean squared error simplifies to just the variance. But this variance may be quite large. Now, in view of this, zero bias is seen as a desirable property, but in the end, the mean squared error determines the performance of an estimator. Now, this means that a biased estimator with a small variance is sometimes preferred to an unbiased estimator with a large variance. To illustrate this, we return to drawing balls from an urn with k-numbered balls. Let x1 up to xn denote the number of balls drawn from the urn. You have learned that estimator 1, twice the sample mean minus 1, is an unbiased estimator for k. And therefore, the mean squared error is equal to the variance of this estimator. Now, to compute this, we cannot apply the rule for the variance of the sum of independent random variables, since the xi's represent numbers drawn without replacement and are therefore dependent. Taking into account the dependence between the xi's, the computation of the variance of t also involves computation of covariances between two xi's. Now, although this can be done by elementary probability theory, this is beyond the scope of this video. But it turns out that the mean squared error is given by the following expression. Now let's consider the maximum of the xi's as another estimator. Now, since the largest number in the urn is k, the maximum of the xi's will always be less than or equal to k. So this means that the maximum has negative bias with respect to k. Indeed, in the previous video, you learned that its expectation is n over n plus 1 times k plus 1. Now, you may pause the video for a moment to check that this is strictly less than k, as long as we do not draw all the balls from the urn. Now, the mean squared error can be computed from its decomposition. Now, this is by no means a trivial computation, but it turns out to be equal to the following complicated expression. On the right-hand side, you see the summation of the variance and the squared bias. Now, we can compare the mean squared error of both estimators by plotting their values for different sample sizes n. Here is the graph of the mean squared error of both estimators. And we see that although the maximum is biased, its mean squared error is always smaller than that of estimator 1. In fact, when we plot the ratio of the mean squared error of estimator 1 divided by that of the maximum, we see that this increases linearly with sample size n. So, the more balls we draw from the urn, the better the maximum performs as an estimator for k compared to estimator 1. Now, to complete the example, recall that we can turn the maximum into an unbiased estimator by inflating it with factor n plus 1 over n and subtracting 1. This is the former estimator 2 in the example. Now, when we add the mean squared error to the former graphs, we see that the mean squared error of this estimator is even smaller, but it hardly deviates from the maximum itself for larger sample sizes. Now, this brings us to the end of this video. In the exercises, you will find more examples of estimation problems in which you can check whether the proposed estimators are unbiased and in which you can compare their performance by the mean squared error. In the next video, we will introduce a first general principle to construct estimators. See you then.